Limits are one of the important underpinnings of calculus, which are going to help us understand how we can look at functions and determine rates of change. But to begin, we need to understand what a limit is. So the limit is a number. It is the dependent value that a function approaches as the independent variable approaches some value. So what that means is we're going to consider what happens to the y value as we get really, really close to an x value. So for some of the functions we look at, the limits are going to be very intuitive and we should be able to guess them. But the idea is that when we get mathematically good at computing limits, we can then look at more difficult functions. The notation when we're looking for a limit looks like this. The limit as x approaches c of f of x equals L. So L is going to be our dependent value that we're approaching. And C is the independent value that we're going to be approaching on the x-plane. So what we're again doing is we're considering what value of y we're approaching as we get really, really close to some value of x. So let's look at an example with some concrete numbers to sort of solidify this idea of what limits are and what parts of this definition are really important. So let's consider the function given in this graph. We have an increasing function that's concave up. It appears to be continuous with no holes or jumps or anything that's concerning here. So first we have to determine which limit we want to find. We have to decide which x value we want to approach. So let's start by looking at the limit as x approaches 2 of our function. So again, we have to pick the value that the independent variable is approaching, and then we want to consider what value y is approaching as we get close to 2. So the word approach in our definition is really important because we're never going to actually plug in 2. We're going to try to get really, really close to 2 to see what y value we're getting really close to. So here, if we pick values on either side, we can then see a little pocket where our y value has to live. So I've picked x values about halfway between the integers, right around 2. So the idea is that we want to get closer and closer to 2. So I get closer on either side, and then I look at what happens with my y values. So here, as my x values got closer to 2, my y values are getting closer and closer to 4. So as my x values move closer to 2 from both sides, from the left and the right, I can see that my y values are approaching 4. Similarly, if we wanted to look at a different limit, we could pick a different x value to approach. So if we want to consider the limit as x approaches 3 of f of x, I'm now asking what y value am I going to be approaching as x gets closer to 3? So again, I'm going to pick values close to 3, and I'm going to use those to see what y values I'm approaching. So I start somewhat close to 3, but then I move closer and closer on either side to where that 3 is. I'm moving up from the left and down from the right, and I can see that the y value I'm approaching is going to be approximately 9. So as I consider limits, I want you to take careful note that I'm getting close to the x value that I want, and I'm getting close from both sides. Now, you may be thinking, why can't I just go to 3 and find the y value? Well, this is a continuous function, so that would work out okay for us here. But with limits, we never actually plug in the value because it's really powerful to be able to find a y value if one doesn't exist. Imagine there was a hole there. We would still be able to find the limit because we never actually plug in the value. Instead, we approach it, and therefore we are approaching the y value. Let's look at a picture where this will be represented. Consider the function given here. F of x equals x squared minus x minus 2 all divided by x minus 2. If we wanted to consider the limit as x approaches 2 of our function here, we notice that at 2, we have this little discontinuity. We have this hole because this function doesn't exist at 2. If we tried to plug in 2 into our function, we would see that we'd have 0 in the denominator, and we never, ever, ever want to divide by 0. So we have to be careful about what we do with this function. However, limits are powerful in that we can get really, really close to 2 without actually plugging in 2. So we want to consider what happens as we get close to 2 from either side. And when we do that, this y value is going to be approaching 3. So here, even though we can't plug in 2 into our function, we can find the limit of what we're getting close to in terms of y as we get close to 2. So even though we can't plug it in, we have some information about how this function behaves. So this becomes really powerful when we have things like discontinuities or places where we would be otherwise not able to plug numbers in. Now, this idea that I'm looking at functions from both sides, the left and the right, is really important. So now let's consider the important things we've talked about so far. Let's summarize them, and then let's do some examples. So the important points so far are that limits are important because they allow us to look at how functions behave even if they don't exist. So we said we could still take the limit even though the function didn't exist at that point. We could still see what we were approaching at that point.